Welcome back. This is AP Chemistry, Chapter 4, Lesson 4, and we're going to talk about the different types of reactions that this chapter covers, and in particular, one of those types. So this reaction is, or this chapter is another hodgepodge or another mix of a bunch of different stuff, and we cover 3 different classes of reactions. At the end of the year, we'll know a whole bunch. Well, we already know combustion, right? But we'll know some other reactions. So first type that's covered are precipitation reactions. And precipitation reactions are simply just wife swapping reactions. They're double replacement reactions where you make a solid product. That's a precipitation reaction. You generate a solid from an aqueous solution. Another type of or class of reactions we'll be covering in this chapter are acid-base reactions. We'll get to those later. I have an abbreviation for reaction. I'm not really sure if you've seen it before, but RXN is the abbreviation for reaction. And then the final type of reaction that's covered in here is a redox reaction. And those are fun. We're going to be balancing some of those later. And yes, that's sarcasm. Okay, so a precipitation reaction is simply a reaction between 2 aqueous solutions. If you think of your lab that you just did, that was a precipitation reaction because you mixed those 2 solutions and you made that yellow solid. Speaking of, remind me that we should reweigh that tomorrow in class. Okay, so we have 2 ionic compounds. They undergo wife swapping, and one of the products is solid. That solid product is called the precipitate. So in this diagram that you see here in your notes, that white stuff is a precipitate. Precipitate is PPT. And if you're not part of the solution, meaning you're not dissolved within the solution, you are part of the precipitate. You are a solid, not an ion that's floating around in solution. Okay? An easy way to look at double replacement reactions is our wife swapping. You cannot call them wife swapping. Another name for these is metathesis. I don't really even know how to spell that, but I think it's like that. So if you have, let's say you have Barbie. She's so beautiful. And she's married to Ken. I don't know how to make him handsome, but I guess that's it. We'll make him smile, because I like guys that smile. So there's Barbie, and there's Ken, and they're married together. Woohoo, they're a happy couple. And there's another couple that lives next door. We'll call her Miley. And, oh, this is a good one. I don't know how to draw him, so I'll just give him a gun. That's G.I. Joe. Okay, and they live next door, and they're a happily married couple. Well, what can happen is they can swing, they can wife swap. So Barbie can kick Miley out of her relationship, and Miley can kick Barbie out of her relationship. So what we would have then, oh my goodness, this is, I can't believe I'm putting a video of this on like TV. This is Miley and Ken with his handsome smile, and they're a new couple. And Barbie with her big beautiful hair and with his gun, G.I. Joe. Now, particularly in this type of reaction that is precipitation reaction, these guys would be aqueous. So Barbie and Ken are ions floating around in solution. Miley and G.I. Joe are ions floating around in solution. And one or both of the products, when the ions get together, they produce a substance that's insoluble. So they'll produce an insoluble solid. For example, in the lab, we took lead nitrate, which is aqueous because all nitrates are soluble, and potassium iodide, which was aqueous because anything that has a group 1 element is soluble. And they swap partners. And so we made KNO3 and PbI2. Again, potassium nitrate was soluble, that's aqueous. That's what some of the crystals are that you're starting to see in your flasks now. And the solid yellow precipitate that you made, that you filtered out, that you calculated the theoretical yield of. Sorry, Jessica was choking. I had to go save her life, but I'm back now. That you calculate the yellow, that we found the yellow precipitate of, that's our precipitate. So we were calculating, I think, the theoretical yield of that. I recognize that my equation is not balanced right now, so I will balance the equation because, you know, we need to be thorough. So there's our balanced equation. So it's just wife swapping these precipitation reactions. You take two aqueous solutions, you mix them together, and one of the products is a solid. Okay? So sometimes we'll be predicting what we make when we mix two things. Remember, when you make a compound, it must be neutral. So you need, if the charges don't add up to 0, you'll need to crisscross them. Most ionic materials will only have one cation and one anion, so a plus and a minus will get together, not a plus and a plus. Notice I didn't make Barbie with Miley. A plus and a minus get together. And then you need to know the solubility rules. Well, actually, you don't need to memorize them anymore. You will be given solubility rules that you need to be able to apply. So you really just have to be able to apply the solubility rules. Okay? So here's some of the solubility rules, and they are found in this reading. You'll note that all nitrates are soluble, there's no exceptions. All perchlorates are soluble, there's no exceptions. Chlorides are generally soluble, except silver, mercury, and lead, etc., etc. So that's how we interpret this chart. Okay, so example number 1, use the solubility rules to predict what will happen when the following pairs of solutions are mixed. Okay. 2 salt solutions always undergo double replacement. They undergo wife swapping. So your possible products are going to be, again, they'll just wife swap. So the Ba will be with the NO3, and the K will be with the Cl. You just swap them first. Then all compounds have to be neutral, so we have to take a look at their charges. Barium is +2, nitrate is -1. Those do not equal 0, so you crisscross. K is +1, Cl is -1. Those do equal 0, so you're all set. So those are our possible product formulas, and then we'll just go ahead and balance, and balance the equation. There's 2 Cl's, so we need 2 Cl's, and then we need a 2 here, right? So now we're balanced. Now, if both of these products are soluble, then you actually have no reaction because these reactants are soluble. So if you could look at the container with your Miss Frizzle glasses, KNO3 would not be together. It would be separate as K plus and NO3 minus. Barium chloride would not be together. It would be separate as barium ions and chloride ions. If we didn't make a solid, then these are still separate ions. So the container would look exactly the same after as it does before, and there would be no reaction. So we'll use our solubility rules. It's always easier to look up the anion than to look up the cation. So nitrates are soluble, there's no exceptions. So this is aqueous. If we look up chlorides, chlorides are soluble except for Ag, Hg, Pb. We're with K. So this is soluble. Well, everything's soluble. All our reactants are soluble. All our products are soluble. So nothing happens. If you mix these 2 solutions together, absolutely nothing happens. We say no reaction. Okay? I'm going to give you another way to look at letter B. If you think of letter B, think about breaking them down first. So I'm going to draw this one. Okay? You have sodium sulfate, which means you have sodium ions and sulfate ions, right? You've got Na plus floating around in the container and SO4 minus. All group 1, any compound that has a group 1 element is soluble. All nitrates are soluble. So this is really lead ions and nitrate ions floating around in the container. So what can you make? Remember, opposites attract. Well, put together this is +2, excuse me, and this is -2. Put together your pluses and your minuses, right? Well, this plus could get together with this minus, but that's what we had, right? This plus can get together with this minus. So that's a new possible product, would be your NaNO3. Another new possible product would be these two getting together, right? Your PbSO4. And what's nice if you think about it this way is your charges are already given, right? But pluses will not get together with pluses and minuses will not get together with minuses. So you have to put opposite charges together and you can't make what you already had, so you have to make new things. All I'm really doing, guys, is wife swapping, right? I'm just flipping them, but I'm showing you how that would happen in solution. There's a chance these two could run into each other, okay? Now, if we look up the solubility of our products, all nitrates are soluble. So this is still going to exist separated as ions. If we look up sulfates, SO4s are soluble except with lead. So this makes an insoluble product. So we made something new and a reaction actually happened. We have a precipitate formed here, and that's what we would expect in this reaction. The last one here, we'll do it the traditional way. We have KOH and FeNO3. They wife swap. So you make Fe with the OH. Again, you have to think of their charges, and you make the K with the NO3. K is +1, NO3 is -1, those equal 0, so you don't have to crisscross. OH is -1. Fe in this mixture, since it took 3 nitrates to make a neutral compound with our Fe, that means our Fe must be +3. Those do not equal 0, you crisscross. Okay? And then you balance your equation here. And I think here. And then we're balanced. Okay? Now, if everybody's soluble, then there's absolutely no reaction. So now we check our solubility rules. Whoops, where'd they go? Our solubility rules. Nitrates are soluble. So this one is going to exist aqueous. It's a nitrate, they're always soluble. Let's look up hydroxides. Hydroxides are insoluble, except with group 1. Fe is not in group 1. Calcium, barium, and strontium. Well, we're not in group 1. So that means this one is a solid. And yes, you would expect to see something happen. You mix these together, you should get this solid, which would be a precipitate. Okay? I think we'll save this stuff for class tomorrow. What we have been writing is this type of equation. The equation where we wife swap and we balance, that's a molecular equation. I will show you tomorrow how to take a molecular equation and break it down into the complete ionic and the net ionic equations. We'll see you tomorrow, everybody.